The graphs of elementary functions. So far you have learned how to graph three types of functions: the linear function, the quadratic function, and the exponential function. While there are many types of functions, by the end of Algebra 2 you will have learned in depth about 12 of them. For this course we will discuss 4 more: the step function, also known as the piecewise function, the absolute value function, the square root function, and the cube root function. Let's talk about the step function. The graph of the step function looks like steps. This is because it is made up of an infinite number of short lines. Let's take a look at this graph a little closely. You'll notice that there are an infinite number of short lines going up on a diagonal through infinity, and each line begins with an open circle and ends with a closed circle. The formula for a step function is f of x is equal to x encased in double brackets. So when you see this notation here, you can say f of x is the step function. The domain of the step function is a set of real numbers, and that includes all the rational numbers and irrational numbers. However, the range is limited to the set of integers, and we denote integers with the letter z, and that's because of the German word Zahlen, which means number. It's also important to note that this is a function because it will pass the vertical line test. The open circles are placeholders, but are not points on the graph itself. So the graph would not exist in two places if a vertical line were drawn at any one of those places. When x is equal to 1, we notice there's only one output right here at the point 1, 1. You might ask about, okay, what about this point here at 1, 2? But that's an open circle. That's a placeholder and is not included as part of the graph. Therefore, there is only one output for this one input. And that's the case anywhere you see an integer value for the x-axis. There's only one output for each input. Next, we will talk about piecewise functions. The step function is just one basic type of piecewise function. A piecewise function is just that, a function made of two or more pieces. Each part can be any type of function. For example, the piecewise function below represents pieces of two different linear functions. So in other words, a piecewise function is a general term for parts of functions or pieces of functions put together. The step function that we talked about previously is a type of piecewise function. The equation for a piecewise function consists of an expression for each piece. Our piecewise function graph has two pieces, therefore there will be two expressions used to represent it. The first expression represents the green line y equals 2x plus 1, but notice how it only exists for x values less than 1. So we highlighted here the part of the graph, which is the green line. We highlighted that, and this is the equation that is associated with that line, and it's only for values where x is less than 1. The second expression represents the blue line, y equals 1/2 x minus 1, but notice how it only exists for x values greater than or equal to 1. So we highlighted the line here in yellow. This is the line, and the associated expression or equation is 1/2 x minus 1, but it only exists for x values greater than or equal to 1. A very special type of piecewise functions leads us into another function. So let's consider g of x is equal to negative x for all values x less than 0, or x when x is greater than or equal to 0. This piecewise graph combines the two linear equations, y is equal to x and y is equal to negative x. So here is y is equal to x. I'll highlight this in blue since this is already in blue. So y is equal to x is this linear portion right here for all values where x is greater than or equal to 0. And for y equals negative x, here we see in green, this is y is equal to negative x for all values where x is less than 0. Graphically, this shows up as a v on the graph, which also represents a new function we're going to introduce, the absolute value function. The graph of the absolute value function is v-shaped. Its vertex is at the origin and is symmetric with the y-axis. Like the quadratic function, the axis of symmetry divides the graph into two congruent halves. Note the graph is V-shaped and it's symmetric with the y-axis with the vertex here at the origin. There's two ways to represent the formula. We can say A of x is equal to ABS of x. This is often used for computer programming or when typing out a solution on computers. Or we can use the mathematical notation A of x is equal to x encased in two vertical lines. Both of these are ways to represent the absolute value function. The domain of the absolute value function is the set of real numbers, and the range is the set of non-negative real numbers. Let's put the absolute value function to practice. Let's evaluate the absolute value of, or a of 17, a of negative pi, and here we're going to solve for x. Given that the absolute value of a number is equal to 9, what are the value or values of x that make that true? Now remember, absolute value, the meaning derives from distance. You're calculating the distance from a number to 0, and distance is never negative. Therefore, the absolute value of 17 is 17. The absolute value of negative pi is positive pi. And in cases where we have the absolute value of a number is equal to 9, there's two possible answers. We could have positive 9 or negative 9, since the absolute value of both of those numbers will result in 9. The square root function. The graph of the square root function is a half of a sideways parabola that starts at the origin. It increases to the right into the first quadrant, as you see here. So we start at the origin, and as we go off into the first quadrant, it's increasing. There are two ways to represent the formula. One with words and letters. For example, we have r of x is equal to sqrt for square root of x. This is commonly used in computer programming, spreadsheets, or where you're typing on a document. The other option is using mathematical notation. R of x is equal to the square root of x, where this symbol is referred to as the radical sign. Notice we're denoting the functions r of x, r for root. The domain of the and range of the square root function is a set of non-negative real numbers. Let's evaluate the square root function with specific numbers. So here we're going to evaluate the square root of 9. Here we will evaluate the square root of pi squared. And this one we're going to solve for x. So knowing that the square root of a number is 64, what was the original number? Based on the graph, and remember we've restricted our domain and range to non-negative real numbers, the square root of 9 is going to be 3. We refer to that as the principal square root. The square root of pi squared is pi. And when the square root of x is equal to 64, x is equal to 8, since 8 squared is equal to 64. Again, we are using the principal square root. The cube root function. The graph of the cube root function includes the other half of a sideways parabola backwards. Its domain is all real numbers. Actually, the domain and range are all real numbers. And all the points are negative mirror images of each other. For example, 1, 1 is a point, and so is negative 1 is also a point. So if we look at the top half of this cube root function here, it does resemble half of a parabola. And if you cut that parabola in half and spin it the other way, you'll have the other half this way, and that's what makes it a cube root function. Like we said, the negative mirror points are going to be 1, 1 and negative 1, negative 1. The notation or the formula for the cube root function is we use c of x for cube root, and we can write it with words, CBRT for cube root of x. This is commonly used for computer programming, spreadsheets, anywhere you're typing on a document. And the mathematical notation is c of x is equal to the cube root of x, where we have a radical symbol, and then this number here is inserted in, that's referred to as the index. That tells you the specific root. Normally with radicals, if there's not an index there, it's assumed to be a square root. Otherwise, we would put a number there to indicate what root you're taking.